Carter here. I recently got one of those cool gamer keyboards with the RGB lighting where you can change the color of each key individually. Now normally people use this to highlight particular keys they use often or show pretty rainbow effects, but I decided to integrate my keyboard with one of my favorite video games, Super Hexagon. You can see how the lighting on the keyboard matches the colors in the game. When I switch levels, the colors change. I can jump into a game here and the lighting on the keyboard matches the way the screen rotates. To accomplish this, all it took was some programming, a little ingenuity, and one piece of secret NSA technology. The way my keyboard mod works is through memory reading. When Super Hexagon runs, it stores information like the colors on the screen and what buttons you're pressing and everything like that in memory. And then I've written a program that looks at the memory, pulls out the colors, and displays the colors on the keyboard. The tricky part is actually figuring out where in memory to find the colors. Games use a lot of memory for all kinds of different things, and the colors we care about are only a tiny portion of it. Moreover, we don't know what format the game uses to store colors, so it can be hard to even work out what to look for. We're going to need to examine the game's code. If Super Hexagon was written in a language like Python or Lua, we could just open it up in a text editor. But it isn't. Instead, the game's developer wrote it in C++ and then compiled it into binary code. Binary code is fast for computers to run, but it's very difficult for humans to understand, so that's where the NSA technology comes in. You see, in between spying on you and reading your emails, the NSA has been developing a program called Ghidra that you can use to open up binary executables and reverse engineer how they work. To download it, we'll need to hack into their mainframe, by which I actually mean go on their website where you can download it for free. So I'll just open up Super Hexagon here. Now we're actually pretty lucky on Linux because the Super Hexagon Linux build comes with debugging symbols. What debugging symbols do is they let Ghidra see what all of the functions and classes in the program are called. So for example, we can see GIF info or FTP exception. A good place to start when we're reverse engineering is in the main function, because when programs run, they first run their main function, which then sets some stuff up and calls some other functions. So if we look at our main function here, we can see that it allocates some memory with this operator.new, and instantiates a game class, a graphics class, and a music class, and then it stores a reference to that memory in the global variable Super Hexagon app. Now looking at this code, I'm pretty sure game class, graphics class, and music class are all part of Super Hexagon's code and not some sort of library or framework that the game is using, mostly because no serious C++ developer would ever write a class name that ends in the word class. It's just not done. So after a bit of digging around, I found this function, draw3dTriangle, in graphics class. Now we can see one of the interesting things that this function does is it calls setColor on an OFX-shaped batch renderer. Now OFX-shaped batch renderer actually comes from an open source library, which we can look up on GitHub, and we can see that the setColor function takes a red, a green, and a blue value, as well as an alpha value, to use to set the color. Going back to Super Hexagon, we can see that it does some pointer math, which might look a little weird if you're not used to C code. Essentially what this is doing is it's using lvar11 times 4, and it's using that to index into an array that's stored at this plus 2978. And then it's using it at 29A0 and then at 29C8. Now, lvar11 is a name that Ghidra came up with. Ghidra actually lets us rename it, so in this case I will call it palette value, because what I think this is doing is it's indexing into a palette. If we look at the differences between the start points of these arrays, 2978 and 29A0, and we pop that into kcalc to subtract them, so we go 29A0 minus 2978, we can see that there's only 40 bytes between the start of these arrays. Now, it's using integers here, and integers are 4 bytes long, so that means we most likely have in memory 10 red values followed by 10 green values followed by 10 blue values for every value in the palette. After a bit more reverse engineering, I found where the rotation angle of the board was stored. So this was a little bit tricky. First I looked for, because we're looking for an angle, I looked for places where sine and cosine were called. I found this help class, another class ending in class, that creates a lookup table for sine and cosine values. So then I used Ghidra to look for places where those sine and cosine lookup tables were used, because most likely they were used to compute the board rotation. In particular, there's this giant compose 3D frame function that does a whole lot of interesting things, but one of the more interesting things it does is it takes this ivar6, which uses game plus 0xcc and dereferences that. I'm going to rename this to what I think it is, board rotation. And then it uses that board rotation, it does some sort of math to it, and then eventually it looks it up in the lookup table. So I thought that that was a pretty good sign that this was going to be the board rotation, and the values we found earlier were going to be the colors. So I actually wrote a little Python script to test this. So let's look at that now. So essentially what this does is it fires up Super Hexagon, and then it uses this special Linux file called procmem to read its memory. So then it looks up those pointers we found, and it reads the values in them. So we can see that 0xcc that we were interested in earlier. So if I actually run this, we'll find that it launches Super Hexagon and displays this debugging display with all of the colors as well as the rotation. So we can look here and we can, do different rotations. We can even go into a game, and we can see that that all works. So that's pretty cool. We now have a way to open Super Hexagon, read its memory, and figure out what the colors and the rotation are. The last step was connecting everything to my keyboard. I actually used an open source program called CKB Next, which is a driver for Corsair keyboards on Linux. It also has a plugin interface that you can use to write plugins in C. So I essentially translated all that Python code you saw into C, wrote a bit of code to integrate it with CKB Next, and there I had it, a cool keyboard hack that was definitely a good use of my weekend.